Hi, welcome to the first part of this lecture. So this is the goal of my topic is normalized volume and supersymmetric profiles. All I'm going to be talking about in this series of videos is based in joint work with Celso Viana. And this first part, I'm going to talk about a little bit of setup from hyperbolic geometry, and in particular, trying to define and give some properties about renormalized volume. Okay. So for the starters, I'm going to be interested in some subgroups of PSL2R. These are matrices 2 by 2 with real coefficients, modulo sign. And what to see in this group is a torsion-free discrete or compact. So what does all of this mean? Well, in particular, if we take here the hyperbolic plane represented here by the bone model, then we can identify PSL2R with the space of orientation preserving isometries of this model. And basically what do I mean by all these use of words is that if I take quotient by this subgroup of isometries, what I obtain is going to be a compact surface. This compact surface we usually refer to them in the literature as being function surfaces. Okay, so this is a very, let's say, down-to-earth construction. So I want to do something a little bit more with that, which is instead of considering just my matrices as having real coefficients, I want to consider them as having complex coefficients. And then once I do that, I mean, my group hasn't essentially changed. But once I consider it here, I want to do what is known as a quasi-conformal deformation. So for what effect I want to do that? So here is the following. So it turns out that as PSL2R can be identified with isometries of hyperbolic plane dimension 2, PSL2C can be identified with orientation preserving isometries of H3. So here, for instance, I have this hyperbolic plane inside this ball, which is representing hyperbolic space. And my group gamma that was acting here in H2, well, is also acting by isometries in the whole ball. And if I will take the quotient, well, the total geodesic plane here is going to quotient to a total geodesic surface, but the whole space is going to quotient into a three-dimensional manifold that topologically is going to be a surface times an infinite line. Okay, so this is the effect that's going to have by considering, by just considering that real coefficients are the same as complex coefficients. And now what that quasi-conformal deformation does is it's going to conjugate the group by some special type of homomorphism, usually known as quasi-conformal homomorphism, so that now we're going to have a group. This group is not going to have real coefficients, not going to be conjugated to a group that has real coefficients, but it's still going to quotient the whole space into a three-dimensional manifold whose topology is still going to be of the surface times a real line. And moreover, this quotient space is going to have what we call a hyperbolic metric. In particular, it's going to be a metric with constant sectional curvature equal to -1. So this type of matrix is the one that we call usually quasi-function. And here in this graph, I'm trying to represent it by, well, a surface that has got a little bit wiggly, that is it's a lot less regular than the surface we obtained here originally. So for instance, just to give an example how more precise is this example is the one that we usually refer as function. And again, when we do the deformation, we call them quasi-functions. As an example, well, if we were going to take the equidistant foliation with respect to the total geodesic surface we can obtain from gamma, and write the coordinates of the metric with respect to the equidistant surfaces, we will write the metric as tt squared plus hyperbolic cosine squared times the hyperbolic metric of sigma. Okay, so this is a very nice recipe for us to generate a lot of hyperbolic surfaces, but we can generalize this story to the following. So I'm gonna try to explain a little bit abstractly, but we are going to see that this theory quite reduces. So I'm going to be interested in M. M is going to be a three-dimensional manifold that has a not empty boundary. I'm going to assume for simplicity that the genus of each boundary component is greater than or equal than 2, and that's so I can avoid something like all of this. I should also have said I'm assuming M to be compacted right here, but I'm assuming so. And I'm going to assume that the boundary is going to be incompressible. So incompressibility means that if I take a curve, a closed curve in the boundary, that is homotopically trivial in N, meaning it bounds a map from the disk, then that curve has to bound a map from the disk so that the image of that map is entirely in the boundary. So in other words, if I can compress a curve of the boundary within the whole term manifold, then I can compress it just along the boundary. So we're going to say that the boundary is going to be incompressible. Okay, with that setup, that is going to make a lot of the description a lot easier. Then we're going to define the set of complex co-compact metrics in M as these are going to be the complete hyperbolic metrics, meaning complete metrics of constant curvature, constant sectional curvature equal to -1, so that each end is quasi-function. So what that means is like what I should have in mind is that M has some complicated three-manifold topology here. Each end near the boundary is going to have topologically is going to have a product structure. And if for each end I take the associated covering space corresponding to this surface group, I will obtain a quasi-function group. So this end towards the end is looking quasi-function, similar to this one, and similar to this one. So these are the space of metrics I'm going to look. And of course, because if I want to consider the inherent metric as the structure I'm looking, not a particular parameterization, I'm going to quotient this space of metrics by subspace. Okay. So it turns out, once I have this setup, that the boundary of M has a well-defined conformal structure at infinity, which again, you know, because the metric is defined up to isotropy, this structure at infinity is going to be up to isotropy. And this structure, if we go back to the previous slide, can be seen as follows. Well, gamma prime is acting by isometries inside of H3, but is acting for conformal maps in the complement of this Jordan curve. So it's going to act compactly in this top half over here to a surface that's going to have a well-defined conformal structure. Similarly for the surface below. And well, only one of these ends is going to correspond to the particular end of M we're going to be interested. And this is the conformal structure we're going to have at infinity. So why is this important? Well, this is important because it helps us to fully parameterize this deformation space of hyperbolic metrics. In particular, we have a theorem due to Alfors-Beers, and I should probably write here names of a lot more people in order to give the description, but it's sort of at least part of the core is due to Alfors and Beers. That tells us the following. This description I'm saying is technically a map that goes from the space of comical compound metrics to the space of conformal structures at infinity model isotropy. That is one of the characterizations of Teichmüller space. So this map is again goes from metric to conformal structures. And well, in particular, what the theorem says is that this map is a diffeomorphism. Teichmüller space is something that well, it has been broadly studied, and in this particular case, because we're looking at compact surfaces, this space is just a topological ball of dimension 3 times the other characteristic of the map. So topologically, it's very simple, and it's telling us that well, we have a finite dimensional parameter space of hyperbolic metrics. Okay. So this is the type of space we're going to be concerned. I'm going to be referring to them simply as complex compact metrics. And along that space is where the functional renormalized volume is going to be defined. So renormalized volume is a real value function from the space complex compact metric that is characterized for the following formula. So I have here a picture for quasi-function manifold, but we can do a picture for any complex compact. But the idea is as follows. Well, each n is going to have some equidistant foliation where the metric is going to be blowing up exponentially. So what I can do is I can rescale by the exponential growth so that now I have a well-defined metric at infinity. This well-defined metric is going to agree with the conformal structure at infinity. And now I can select something. And now I can select the following. I can select a very special equidistant foliation so that this particular metric at infinity constructed this way is the hyperbolic metric in the conformal structure. So here, by uniformization, given any compact conformal surface, there is a unique hyperbolic metric in that class. So this full is going to characterize this foliation, this equidistant foliation at infinity. And then I'm going to define the function of renormalized volume as the volume interior to the R leaves of each n minus 1/4 the integral of the mean curvature pointing inward along the surface sigma r plus a linear term in terms of r that depends only on the other characteristic of the boundary. So just to remind you, well, here I'm considering the mean curvature as the sum of all the principal curvatures, so that the variation of area can be calculated by this formula. And if you're attentive, you can note that the right-hand side of this equation is technically depending on R, right? Because here I have a full foliation, I don't have like a particular level. So it turns out that after grading the variation of formula for this nice application on Gauss-Bonnet, is that this right-hand side does not depend on R. So I can call upon any R in order to define this quantity and calculate renormalized volume. So you do this for any complex compact metric, and this is how you obtain your renormalized volume. So to make things clear, let's take a quick example. So I'm going to assume, again, that my surface is going to be Fuchsian. And in this case, it turns out that the foliation that you will obtain, so you have a hyperbolic metric at infinity, is the same foliation as from the totally geodesic surface we had in the middle of the function manifold. And moreover, that totally geodesic surface comes as the level 0 of your foliation. So now, if I evaluate then for R equal to 0, the definition of a normalized volume, then you will see, well, here, once I replacing this formula, because my full figure is collapsing to a totally geodesic surface, both the volume encapsulated by the R leaves, their mean curvatures at the R level, they all vanish in the formula. So we have the, well, renormalized volume of a function manifold has to be 0. Okay. So part of interest of renormalized volume is that as a functional, it has a relation to another functional that has been studied for complex compact metrics. And one of the highlights is that it has nice analytical properties. And for context, and also because it's going to be relevant for a later part of the talk, let me tell you the following theorem that was proved independently by Bridgman, Brock, and Bromper, and also by myself around 2017, that says the following. So let's keep assuming M as we have so far. I want to assume M to be hyperbolic with incompressible boundary. Then renormalized volume of M is bounded below by this quantity, B3/2 times this number. Where here, what this means is the following. Dn is the double of M. So whenever you have a manifold with boundary, you can construct the double by taking 2 copies of them and gluing the boundaries by the identity map. That's now going to give you a closed manifold. These 2 bars here, these denote the Gromov norm of such manifold. So this is a topological entity of your tree manifold. And V3 is the volume of the regular ideal tetrahedron, which is a fixed volume in 3 dimensions. So we have to grade here this somehow different quantity from renormalized volume that we were studying. But maybe a good way to understand it is the following: is that if the double of M, if this double, or it will happen to be a hyperbolic manifold, meaning it accepts a hyperbolic metric. Because of Mostow rigidity, we know that that structure is essentially unique. And V3 times this Gromov norms, this is exactly going to be the hyperbolic volume of the double. So this is basically saying that renormalized volume of M is always greater than or equal than half the hyperbolic volume of the double. Moreover, that's in terms of this inequality. And this inequality is charted in the following sense: that equality is realized by making the ends of M function. So this means that in order for this equality to happen, in order to have a sequence of hyperbolic manifolds so that this distance goes to 0, then what should happen along that sequence is that you are making each end to be function. As a nice simple example, or as a nice corollary of this, is that if we take the renormalized volume of a quasi-function manifold, well, in the case of a quasi-function manifold, this Gromov norm of the double is just going to vanish. So it's just telling us that the renormalized volume of quasi-function manifold is greater than or equal than 0, which is exactly the renormalized volume of a function manifold. And the sharpness of inequality tells you that inequality occurs if and only if the manifold is function. Okay, so I'm going to stop here in terms of regarding general knowledge about renormalized volume. And the following talk is going to address isoparametric profiles.